thank you very much for the introduction, and thank you for the invitation. It's always a great pleasure to come back here at ETH and talk about our research. How the talk is structured, actually what I would try to use a morning session here to discuss more the basic and the principles, and as we have a second follow-up session just after lunch, there I will show a little bit more how we apply the PRM and actually move it to the next level, what we call PRM version 2, and it has mainly as a goal to not only small quantitative assay, but large scale, looking at hundreds or even thousands of peptides in one single experiment. But what I'd like to do today is just go through the basics. I know you already have the course for 1.5 days, so maybe some of the first slides is kind of a recap of what you have heard before. But I'm just taking a little bit historically and see why targeted proteomics have moved from the classical SRM type experiment into high resolution accurate mass. And that's basically what I would like to discuss, and show some of the immediate benefits of using PRM, which are mostly, there are several, but the main ones are the selectivity and to some extent sensitivity, because we're no longer operating with in-beam system where you can just measure a flux. We have trapping devices, which means if you have small amounts, small fluxes, you could trap for some time, some amount of time, and dramatically boost your sensitivity in that way. I'll show you an example of that. So we're talking here quantifications, and so maybe I have to move in front of my screen. What are the criteria or features you need to have if you do a quantitative assays? First of all, you want to have selectivity, sensitivity, and then to some extent you need robustness, because a quantitative assay is by definition not one or a few experiments. It's usually a large set of measurements you need to repeat. So your instrument, your setup, your method have to be robust in order to get reliable results, not only in the experiment you perform, but over time. So in terms of selectivity, the main challenge here is we're dealing with biological samples. Are they cell lines? Are they bodily fluids? We have very complex mixtures of proteins, and at present, we cannot really measure proteins in proteomics. I mean, it can be done in top-down approach, but certainly not in a routine and quantitative way. So the only practical way to actually measure peptides systematically and properly quantify them, proteins, and quantify them properly is at the peptide level. So a complex protein mixture, we digest, we generate a very, very complex mixtures of peptides. So that means we'll have coeluting species, we'll have interferences, so we have two ways to address the problems here. Either we reduce the complexity, I'll show you one example in the afternoon, there are many different ways of doing that, or we try to get better instrument with higher peak capacity, not only on the mass spec side, but also on the LC side, so you could better separate your peptide first, and then even they have silly masses, your instrument can then eventually segregate these different masses and ultimately separate the analyte you are interested in from the background of the matrix. Second issue is sensitivity. You all know that we're trying to quantify peptides over a large range, so depending on your sample, but 6 orders of magnitude is not uncommon. If you're looking at blood or other samples, it may even be 10 orders of magnitude. So you have to have a huge dynamic range, and some of the components you want to measure are actually relatively low concentration. So you need to have sensitivity. So that's here where limit of detection comes into play. And if you have a background, that background is often the limiting factor. So often the claims of the manufacturer's brochures, you have very good sensitivity. It's measured on individual components, but not necessarily in a background. And then background is really one of the issues you control. And you will see in the example I'll show you later how or why resolution and accurate mass is important. And the last point, robustness, already mentioned that before. You try to measure a larger number of samples, you want to be able to reproduce your data. So what you want to do is, first of all, multiplexing is measure as many peptides as possible and quantify them properly. And you need throughput, because if one experiment would take 1 day, measuring 100 samples would take a bit a long time. So eventually what you want to have is a relatively fast setup, so you can have the analytical throughput needed to do, let's say, for clinical studies. So these pictures you've seen, or similar one you have seen in the previously, targeted experiments are done in SRM mode, where you select your peptide, typically a doubly charged species, you fragment, and sequentially you measure one fragment ions at a time. You can measure several fragments, typically 3 or 4 for each peptide. If you do quantification, you have your internal standard. You measure the corresponding fragments of your internal standard. You get these ion chromatograms here, and then you quantify, as it was shown previously, using the area under the curve, and then all the rules Christina and probably Brenda have discussed with you already. So back to the basically triangle we have to cope with in quantitative assay. You need sensitivity, selectivity, and what we call scale here. That means how many analytes can we measure in one experiment. And you try to get all of this at once, which is kind of a real challenge. Right? So often we have then to either compromise and say it is a quantitative assay, we focus on sensitivity and selectivity on a limited number of peptides, or we try to measure a lot of peptides, and that will have some consequences on the other parameters. And this is summarized in this slide here. To keep things simple, we can say there is basically 2 types of experiments. And you can imagine anything in between, but to be relatively systematic, let's say we do a classical quantitative experiment where we try to quantify, let's say, 12 or 24 of peptides very precisely and accurately. In that case, the scale is not really an issue, and scale means eventually cycle time and all number of parameters we need to adjust. But we can really set up our instrument, our method, to get high sensitivity and selectivity. The second type of experiment is more the kind of primary screen, where we have a relatively, typically in biomarker, or you're looking at pathways, you have a large list of candidates, and the question is there, are they present in the sample, are they activated or expressed, and get some orders of magnitude of the level of expression. But you do relative quantification, you don't necessarily to try to quantify very precisely. And since it's a primary screen, you can allow for false positive, which you will go back. So here you will privilege scale at the expenses of selectivity or sensitivity. So in an SRM, for instance, you would look at less transitions, but more peptides. And your data may be not as clean, but it is a primary screen. And I'll show you in a moment how we try address the same questions using PRM. But that is just to set up the background and the stage and what we try to define in quantitative experiment. So a targeted experiment, as you have seen so far, right? You start with a list of proteins. You have hypothesis. You're interested in a list of proteins. You select the peptide, prototypic, quantitypic peptide that was described. And then you have to define your method for your triple quadrupole, which basically means you need to define the fragments, ions. You need the precursor, the charge state, when they elute, collision energy, and all these parameters. So it is actually a fairly long and tedious process, because you need either to have already your spectra, your peptide measured, or you have to go to a database and you build your method. It's a very good tool to do that. You can do the method, and eventually you build the method, you upload to the method to the triple quadrupole, you measure, and you get your data. So you've seen that. I will not discuss it any further. One important parameters for all quantitative experiments is actually the collision energy. There is a default value, which works in most of the cases. I'm not going to discuss that in much more details, but I just want to make the point here. If there are some fragments which are labeled, such as proline cleavages or B ions, that not always have the same maximum as the classical Y ions. And that may have to be taken into account in some instances. So the classical way of doing this experiment, you collect your fragment ions, you can quantify it. Eventually, if you have enough transition, you could look at the different ions, represent them in a spectrum, and looking at the ion ratio, right? To use, in addition to the pure quantification, using this pseudo spectrum, if you will, to make sure you have the right analyte. And this is what is regularly done in small molecule work. Not only you quantify, you have eventually to verify that what indeed you're measuring is the right analyte. And I'm insisting on this point right now because here it is not that simple to do it in SRM. It's an indirect way, but in PRM actually you get it for free. And I will come back to that point a little bit later on. But not only quantification is important, you need to make sure you're actually measuring the right analyte. So overall, the workflow is the following, right? You build your method, you collect the data, and then you quantify and you look at the traces. So this is very generic for targeted experiment, and now I go further and I try to show you how we implement it in the context of a PRM experiment. So for the data processing, I'm not going to discuss it. There is many sessions in this way here. So in SRM, you get your data, you use skylines, and eventually the result, you can then download, process it, do statistical analysis. We try to build a similar workflow for PRM, and I'll come back to that in a minute. So I think I've already pointed out all the benefits of SRM. There is a few limitation with the technique, and the technical one is both the quadrupole used for the precursor selection as well as the second or the third quadrupole, in fact, used for the selection of the fragments are low resolution, so nominal mass 1,000 or 2,000 resolution, right? So that is quite a limitation if you have multiple species coeluting, and I'll show you an example. And eventually, you have to cope with the duty cycle. If you want to put more transition, basically, if you keep the duty cycle fixed, more transition means less peptide. So you have an issue with selectivity, potentially. And this is kind of showed here, right? Often the signal we measure in an SRM experiment is the red one. What the signal is, and I show you example of that in a second, that in blue is what you want to measure, but there is other near isobaric species coeluting and they merge together, and then what you measure in terms of over here the curve is not exactly what you have in your sample, but is more because you have interferences. And this is one example, try to illustrate that. That's the blood samples, actually a peptide of blood. This is the internal standard, so isotopically labeled at the C-terminus. We see here nice transitions. This is everything you expect. The ratios are correct. But as if you drive in north of France or in Belgium, you often see that sign when you have a railroad crossing, meaning that stop, watch twice, because a train can hide another one. And that's exactly what happened here. I can indeed, if I look here, find my peptide of interest. And this is already PRM data. I'll show you the SRM data later on. But you see, if you would just look in the regular windows, actually there's a lot of other ions or fragments interfering, and if you're not very careful, you may very easily do the wrong quantification and come to the wrong conclusions. So that's why we tried to move to PRM using high-resolution instrument, and we've done most of it on a Q-exactive or Q-exactive type instrument. So basically, it is an Orbitrap instrument in which you have a first quadrupole, which does exactly the same function as a triple quadrupole instrument. Right? So it selects the precursor here. The geometry is a little bit different here. The collision cell is in the back, but that's only for practical reason. You get the fragments ions here, and eventually you can measure your full spectra here. The point I want to make here that you have high resolution here, so you will have a very simple, well-separated fragment ions. The experimental design, as I discuss a bit later on, is much simpler in that we don't have to put all the parameters we have described before. We only need the retention time, or the elution time to be precise, and the precursor ions M over Z values. All the other parameters can be used subsequently. And we can actually do two experiments. We can either measure the fragments after getting fragmented back and do what we really call PRM mode, but you can also isolate in high resolution the precursor ions and use them doing very precise quantification. And I'll show you an example of that as well. So what we try to do here now is use the high resolution and accurate mass for, first of all, increasing the selectivity, as I mentioned before. Then we can better discriminate the action analyte from the matrix. And in addition, we fragment all the precursor, all the ions are in the collision cell, and then subsequently pushed back in the envelope. So we get all fragment ions measured at the same time. So we don't have to pre-select which transition we want to do. We collect all of them, and post-acquisition will do that. I already mentioned there are trapping devices, so we can exploit them to increase sensitivity if we need to. And so there is a multiplexing capability. I'll briefly come to that later on. I'm not sure I have enough time to go in all details to discuss that, but at least I will show you the principle. So this is a simplified version. Actually, I should have shown that slide before the QExactive layout. It explains much more clearly what we try to do. So the front end, except the technical difference, difference that we have the collision cell at the end. But in essence here, this is very similar in principle to a triple quadrupole SRM experiment. Right? Selection of the precursor, fragment ions. The difference here, we measure all fragments ions at once. And post-acquisition, we have all these spectra, and we can extract the ion traces. So the difference here between this type of experiment, a classical, let's say, DDA experiment, we do a targeted experiment. So we will record a full MSMS spectra during each cycle. That means every 2 seconds or so. So we systematically collect the data, and then we can try trace the intensity over time. So we can really properly quantify. And this is different from a, let's say, data-dependent experiment, where basically you detect the signal, you trigger once or twice, and then you move on, right? You have only partial quantitative data. Here we have a full set of quantitative data, and then you can, post-acquisition, extract the traces of interest. And that is the actual important factor here. So you can basically split your method in two methods, one for acquisition, where you define very few parameters, the mass and the elution time, and then you process post-acquisition. For that, you need to define basically the extraction window and the fragments ion you want to extract. So I guess this we have discussed. I can skip on that. And this is now summarizing how you define the method. Very quickly now, you could skip a lot of steps here. You basically have your peptides, your precursor masses, collision energy, which is set by default or some general rules I'll discuss a little bit later on, and the elution time. And there is a couple of instrument parameters which we'll discuss later in the day. It's basically the resolution of the instrument, which also impact on the duty cycle. As already mentioned, you can eventually basically do two types of experiment. Either you just look at the precursor, and you can use the signal of the precursor, which you measure also every 2 seconds or so, and quantify on the precursor. And this is doable in this sense because you have relatively good resolution. Even you have multiple precursors, they can be resolved, and you can do relatively good quantification, and you can use quite high resolution to separate the different isotope and the matrix. The other way is do a classical PRM experiment, where typically if you quantify, you have an internal standard, so you look the signal of your endogenous peptide and the so-called heavy fragments of your peptide, which has been added as synthetic peptide after the digestions. So this is, once again, the workflow and the different step. You isolate one precursor, you fragment it, and then eventually you push collectively the fragments into the Orbitraps. And while you measure the full MS spectra, you can already start and do the next preparation of the fragments ion, if you will. So you have really the two instruments or two layers of the instrument can work in parallel, and you can max it out. It has some constraint on the duty cycle, but I'll show you that. I'll discuss it later on. But in essence here, you have one step isolation, fragmentation, and the second stage is measuring the fragments ion, and these two things can go in parallel. So this is an important point here. Also, for the multiplexing capabilities, you could actually, especially if you quantify and augment the duty cycle, multiplex. That means you isolate the precursor of the peptide of interest and its corresponding internal standard. You collect all the fragments together, and then you measure them collectively. And that works out as long as they have different masses. Show you an example in a minute of that. So overall, and that's the point I would like to make here, is to summarize at this stage here. We collect full MS spectra on a regular basis, so we can then use them for quantification, but we're not using anymore the classical workflow, first quantify and then verify. What we can do with this mode here is actually apply the rule. First, we check our MS spectra. We make sure the peptide is the right one, and I'll come back to that in a moment, how we actually do generate the reference spectra and a reference fingerprint, if you will, and use that as a first quality control. So, but the point here, or the workflow here, we're using the MS to confirm that we have the right peptide, and only if we are sure we have the right peptide, we actually move and try to do quantification using the traces of the fragment ions of interest. And just to illustrate the point of the MS spectra, and you'll see later on, or this afternoon, why that becomes important. If you look at MS spectra measured on different instruments or a slightly different condition, they all look alike, but if you look at the intensity, there could be quite a bit of change in the relative intensity of the fragment ions. And now if we want not only use the masses of the peptides to make an identifiers, but we also use the intensity or the relative intensity, it is quite important that we define exactly the conditions. And in some of the large set or large scale experiment we'll discuss later on, it is quite important that you actually make sure that the reference spectra are measured on a platform under similar or same conditions. So you can actually use the reference spectra to do some quality control and decision during the process, as we discuss later on. But this is an example here where we have the internal standard and the endogenous peptide under the same condition, and this is how it should look like if you compare the spectra either to spectral matching, dot products, or other measure. They give you basically similar, very small differences, and this is quite important for some of the experiments we'll do in the subsequently. So what I'd like to do here first is quickly show you a couple of examples how we can actually use a high resolution precursor ions. So instead, we just collect the ions in the seed trap and then push them in the Orbitrap. So this is some of the first experiment we did with that technology. And the point I want to show here is actually how that helps to actually get better quantitative data and boost sensitivity. And long story short here, so this scheme here typically shows you the process from the previous slide, right? This is the different stages. You collect the ion, eventually put the Orbitrap. So this is the quadrupole, the storage device, and then the Orbitrap. So if you do a full MS spectra, as we do with any instrument, what you see here is actually almost every mass along the spectra is occupied with a lot of signals. And if I'm more specifically interested at this low mass peptide here, actually you see that they represent only 3% of the total ion current. Now, we working with trapping devices, that there is a maximum number of ions we can put in, So we had a lot of junk or other things we put in. We'll saturate the system, which is not relevant, and what we try to measure may very quickly have a very limited dynamic range because we cannot get enough of it. Now, if we use a quadrupole to cut out exactly the small band we want, we can now increase and only isolate a peptide of interest, and now we can boost dramatically the sensitivity of the system. And this is shown here in full scan mode. So we're looking at a couple of peptides, right? We would have a limit of detection of quantification very high here because the reason I just showed. If now we isolate only a small windows, we can basically extend the limit of quantification quite dramatically because now we can really focus on only the ions of interest. And I'll show you later on how we do it in PRM using the same kind of approach, and how beneficial it could be then to be able to isolate very small amount of ions versus very large windows. Now, if we move to the PRM mode, so the one I'm sorry, wrong button. So the PRM mode, fragment here, and then collectively push back the ions through the C-trap into the Orbitrap, right? So this is the principle. Now, there are different ways you can do this kind of experiment, and I'm not going into the all details. All that have been published in the first paper, MCP in 2011. We describe the method, but we actually can differentiate different methods how actually to do this sequence of isolation, fragmentation, and then detection. And the first one would be the first one would be this one here, the natural, right? You isolate a peptide, you fragment, you measure, and you isolate the second where you measure first one, and you measure it, and so on and so forth, right? So that's just probably not the most efficient way, in that the Orbitrap needs more time that you need time to get the ions from your peptides, right? So this is certainly not the most efficient way. So a better way would be multiplexing, where you isolate, let's say, 2, or you could isolate 3 if you wish, or 4 peptides. So you max out the isolation with and synchronize it with the detection time. So in that sense, you will optimize your method. The other way is you could measure several peptides at once by using larger windows, with a few caveats there, in that you get co-isolation, but it can also have some advantages if you want to measure several peptides. So this is, again, the two most common methods, the sequential one, or here multiplexing these different ions. So just a couple of examples to illustrate what I just said. If you go sequentially, you would, for instance, measure the light peptide. You'd get this one here. You measure the heavy peptide. You get this set of signs. And if you get, then you process exactly in the same way if you would do an SRM, extract this ion, so far. In this case here, you get a convoluted spectra in which both the heavy and light ions are measured together, right? The difference, instead of having 2 spectra, 2 acquisition, you have 1 acquisition, everything inside. But that's just a question of software at the end of the day to extract the traces and do the quantification. And that is very same way, right? We do not quantify on the spectra alone because there might be changes. We still go back, extract the traces, and quantify across the entire profile to have a precise quantification. So sensitivity, I said, it's an important factor. So this is one of the points I quickly want to go back and try to discuss it with an early example of it. And it was a little bit a complicated experiment, but that was the only way we could really try to assess how sensitive we could be. So typically, if we just do a dilution curve, when we go very low dilution, what happens, most of the peptide or the analyte will stick on the column or will get lost and never reach the mass spectrometers. So what we did here in order to really assess the dynamic range and the limit of detection, we synthesized a series of peptides. We did this, and there is a second experiment with a different sequence. But what is here is different peptide, the same sequence, if you will, with different labeling. So red means there is carbon 13 instead the regular carbon 12. And we have a series of them at different concentrations. So we can mix them. If we mix them 1 to 1 to 1, we get this kind of spectra here. But we can also mix them at different concentrations and get an in situ dilution curve. So that's basically what we have done here. This is some of the instrument parameters. I skip that for the interest of time. And what I can show you here, I think all that has been published. You can go back and read it. But the end result here. So basically one peptide, this one was always injected at a relatively high concentration, 20 femtomole, and it's kind of a carrier. And the second one here was diluted progressively to very low concentration, suboptimal. We're talking zeptomole here. And then we measured in PRM mode and in C mode, how low can we go and still detect a reasonable good signal. And here you have at 0.03 attomoles, 30 zeptomole, you see you could still properly quantify that peptide. I'm not saying it is a routine experiment you can do, but it really shows that if you need sensitivity, you can get it because you have a trapping device and you can collect the ions for a longer period of time. So the price to pay here is that we collected this very, very low amount for almost 3 seconds, right? So this is, you cannot measure a lot of peptide at this level of sensitivity. But if your experiment is really geared to get a few peptides in very, very low amount, you can actually tune and design your experiment in such a way and use a trapping device to improve your sensitivity. And these are the raw data used for that experiment. This is looking at, first of all, the precursor. So you have the different concentration, and you have here the ion chromatograms. So you see if we do a control blank, really no signals. And if we go at 90 zeptomoles, we can see signal to noise at the edge of detection, but at 200 zeptomoles, you can properly quantify it and detect it. And the same thing applies if you look at the MS, looking at 2 fragment ions, while control, no signals, low concentration. We can start detecting here at 270 a very good signal to noise. Again, you need time to use this measurement, but it shows you that you can really go in the sub-attomole if you want or you wish to. The next point here is there's also one of the early studies we did. We compared for a number of peptides. So we had the synthetic peptide we put into urine sample in that instance, and we basically compared the method PRM versus SRM. Same sample, same HPLC, same front end. So we just repeated the experiment on both platforms, and then we looked at 175 transitions. That means that for the signals of 170 fragments, we try to assess the best we can with using all kind of quality control, which one are pure signal compared to those which are potentially interfered, right? And try to make a call where PRM outperform SRM. So we've done several in the meantime, and the figures could change a little bit, but in essence, in 2/3 of the time, you get better result because you have more resolution, better selectivity. In some cases, we get similar result, and in maybe 1/3 of the time, also 20% of the time, you get a better or slightly better result in SRM. And this is mainly due to the fact that usually there is very little background, and SRM uses its full duty cycle to do that, versus PRM has a standard, at least in that setup, a standard setup for acquisition, which not necessarily favor always the highest sensitivity. So back to selectivity of measurement. This is one example. This is actually the slide I showed you at the beginning to put the point of the background. So this is a PRM experiment of the internal standard, and you see here it's what we do expect. In SRM, you see, you may see the peptide is all right, but if you look at the ion ratio, you already see that there is a little bit of questions mark or the ion ratio not exactly what they should be. But this is the internal standard. We don't worry too much about that. That's what I showed you previously, and now this is SRM versus PRM. And this here, in SRM, the endogenous here, you clearly see, you see a big interferences, and the actual signals of interest are somewhere low here. You may detect something, but I would not be very confident in what you measure in that case here. Here in PRM, clearly you have also many components, but now you can really make the call. If you know the time, you get your signals, you look at your ion ratio or your MS spectra, and you are quite confident that you're measuring the right thing. Right? So the point of having interferences in low resolution mass analyzer is not uncommon, especially if your sample are fairly complex. And this is back to the slide I've discussed before, right? So if we try to quantify, we now try to optimize these parameters, and we have done a trade-off. We didn't really try to get as many peptides as we want in the experiment. So again, one more example to show you the point of the selectivity. And this is another parameter you can use. Here I illustrate it on the SIM mode, but the same applies for the fragments ions. If you use the QExactive Plus instrument, so the different instrument from the family with different resolution depending on the generation, but the point here, you have a tunable resolution. That means you can, if you put more time to do the measurement, get better resolution. And what I try to show you here is on SIM mode. Here, actually, this is the peptide we try to measure, and that is the signal we do see. So if you do an SRM, or you will select that, for sure you would isolate these ions here, but the actual ions with the right mass is that small shoulder here. So right, clearly here we have 99% or 95% of the signal, which is a contaminant, probably a C13 or another peptide. And this is, if you zoom in here, at nominal 70,000 resolution, you can't really properly measure it. However, if we increase the resolution, we can now clearly separate these two, and this is now here, right? See, even if there is another species nearby, higher resolutions allow you to properly quantify it, and the result here in terms of if you do the dilution and see how far you go, right? In that instance, you're limited here, but if you increase your resolution, you can certainly go down and improve further your selectivity. So you have the options. Not only it is high resolution, but it is a tunable resolution from anything from 15 or 20,000 to 200,000. And you'll see there is a cost of it. It's basically the transient time. But depending on what you want to do, you can play with these parameters, right? And that's back to this scheme here. The more time we will put or increase selectivity, then will it potentially affect the scale. I think one other example of it, but I can probably keep it short here. I think in the meantime you're convinced that you could see things in SRM, but the signal doesn't necessarily mean it is your peptide of interest. This is another example where we look at different transition, and if you look at synthetic versus endogenous peptide, you clearly see that you sometimes have they don't correspond that clearly. If they don't correspond, means one or the other of the transition, either in the native peptide or in the labeled peptide, there is another signal interfering. So the last thing I try to do in this module here is compare SRM versus PRM. And this is one peptide, two transition here. if we look at these traces, it is very obvious from here there is interference of the two species because they don't collude, right? So the QC tell you right away there is a problem here. This is now the PRM experiment. So PRM, we collect all the data, and what we've done here in the data processing, and that's an important part of the data processing where you extract the traces. One thing you have to define is the windows by which you select your ions, right? We're measuring typically with very good mass accuracy, 5 ppm or less, and that's the point I haven't discussed yet, but not only we measure in high resolution, but we measure in accurate mass. So that means the precursor ions and the fragment ions, we have them at the millimass level precision. So we can use that information to make sure we're actually measuring the right peptide and not something else. And that's what I showed you on the previous example with this SIM spectra where we had the values allow us to differentiate that. So that means we have very high resolution accurate mass. We can extract our fragment ions within a window, and typically we would probably use 10 or 15 ppm as tolerance and measure that. Now, if I use a broader window, and this is just as a model, I can open it to, let's say, half a Dalton or nearly a Dalton, let's say 700 ppm, which is more or less mimics the windows or the resolution of a quadrupole, the third quadrupole of the triple quadrupole instrument, where I extract my precursor, my fragment ions, sorry. And look at the picture here. This is reconstructed, right, from the data, but it is very similar to that one, right? So here actually we're quite in agreement, and we can say there's a second species which collude here. However, if you now tie down your extraction window to 10 ppm, and you really extract the fragments ions you want to extract, right, to these windows here, you get actually quite nice coeluting peaks, and you get your two fragment ions. Now, not only we collect the traces, but actually we collect full MS spectra, right? Now we go down. It's not the full spectra, it's only the range here. So this is basically collecting the spectra of this region here, right? And what I see here for the first spectrum, the green one, the blue tray here, this is the fragment ions and the corresponding C13. And I have a second ions which actually is a little bit of an impurity here. You see even that peak here has already an impurity, and this is even with better resolution. If I look at the second traces here, the target, which is the green one, is actually the minor component here, and it's dominantly this interference here, which is C13 of that other peptides colluting here, right? So if I extract with a large window, or I do an SRM experiment, I'm mostly measuring the interferences, right? And this is what we see here. Now we can look at the masses. We have the exact masses of these interferences. We can re-extract all of that. Now we see we have our perfect coeluting, and we see that the second species is actually eluting later, and we even know the mass of the fragments ion. Right. So that really indicates you not only you have a tool which is more selective, but you can actually use a tool and go back in your data if you have interferences and try to understand what is behind and is your data. And in terms of getting selectivity, and this is my last slide on this topic, we can actually do two things. Is either use a higher selectivity on the Orbitraps. It's one way you can tune your selectivity, but also with the latest generation of instrument, the quadrupole is actually very performing, and you can work with different isolation window. The default initially was 2 m/z, so which was relatively broad. Now we can go to 1 or half m/z, and actually that helps as well in getting better selectivity. And to illustrate the general principle here, it's quite a long experiment. It was looking at a large number of peptide and 2,000 fragments, and it was pretty much a systematic scan looking at different windows from the quadrupole, so somewhere fairly broad, and on the other hand, try to look how does it affect also the Orbitrap. So you get obviously maximum selectivity if you get a small window, and we can even go further down now here, even increase that to 140, but all has a price in terms of sensitivity and selectivity. But if you try to get optimal conditions, let's say in that region here, you see that you have less than 10% of your fragments are interfered. Now, as soon as you relax either the windows of the selection of the precursor or the Orbitrap, you see that you get quite quickly a larger number of interferences to 20, 30, and even your very relaxed condition, you can get half of your peptides or half of your transition have actually a contaminant into the spectra. So I think I covered most of that so far. I try now to spend a couple of minutes to how can we try to measure more peptides, and we have to compromise a little bit on some of these parameters, right? And this is a typical scheme of an SRM experiment, where basically you have the dwell time, the number of peptides, the number of transition, and you have to combine them and find an equilibrium for corresponding to the type of experiment you try to do. What I try to do here is how do we translate that now in a PRM experiment, keeping the same ideas. And what here means scale the number of peptides we want into the experiment, and now how do we tune sensitivity and selectivity? So sensitivity, as I showed you before, is basically the fill time. How long do I need to trap my ions to get enough signal so I get a reasonable MS-MS spectra or an MS1 signal? And selectivity is how do I tune the resolution, which basically means the transient time, right? On an Orbitrap or on a Fourier transform instrument, you measure the image current. The longer you measure it and you do the Fourier transform, the higher your resolution. Basically, this is the length of your transient, which controls your selectivity. So how do I control that? And remember, that's why I spent some time before to show you have those two layers. You collect the fragment ions here, and then you pass them and you measure the MS-MS where you do the other one. So the most efficient way is if these events have equal time, so you perfectly synchronize them and you have the best duty. And what we try to do here is to show if we synchronize, if I increase the resolution, it gives also me more time to collect ions. So the sensitivity and selectivity goes hand by hand. So this is basically, the whole question becomes now a simple question of balance between performance and scale here. And we don't have to work in the triangles because now it's just a balance between basically resolution, transient time, and number of peptides I want to measure. So this is a complicated table. The numbers are different depending on the platform you're using, but in essence, what I try to show you here, you can really limit the discussions to a very few number of parameters. The resolving power, resolution, and transient time are the same. It's not the same thing, but they go together. So this is the nominal resolution, that's the corresponding transient time. The fill time or injection time, we try to synchronize them to be most efficient. And if we multiplex only one time, basically we see here that if you assume for chromatography, which is classic nanospray, we have a 20-second peak width. We want to quantify with 10 peaks across the peak. That means 8 to 10 points across the peak. We can back calculate, or 2 seconds divided by 120 give you 8 peptides in 1 2-second cycle, right? So that's the way how many you can measure. If you duplex, that means you could get, that means you measure 2 precursors at the same time. You could measure twice as many peptides, very logical, but then the fill time will only be half, right? Because then you will use your fill time half for measuring the first one, half measuring the second time. So you can tweak it that way. But basically, it shows you that at the nominal resolutions, and if you set that, you can get somewhere between 8 and 15 peptides in one experiment. And this is, if you schedule then your measurements you do in SRM, every window you can do or use the same kind of parameters. And I will discuss that a little bit more details after lunch. And I show you actually how we can do that a little or significantly more efficient, not only just by applying a default method, but actually doing on the fly that the system can recalculate depending on the parameters and optimize. So we have optimized sensitivity and selectivity. So I'm not sure I went too fast or I was too fast. So here I can wrap up this first section here, and I try to summarize the strategy for targeted proteomics and try to compare it in a summary way how we do an SRM versus a PRM experiment. Right. The main differences here is that here we have different hardware. Here we measure a flux. Right, the front end is the same in essence. Here we measure a flux. The analyzer is static. We have to preset them, and then we measure the traces one by one. Right, so this is a sequential event. If we do a PRM experiment, the device is slightly different. We have trapping devices, and I showed you the benefits of a trapping device. It has also some limitation, right? Because you have very easily saturation. So this is not as, and that's why sometimes defining this method is a little bit more tricky than a standard in-beam, because if on a triple quadrupole you inject more, you get more signals. At some point you may start getting saturation. Here is not just injecting more, get you more signal. It's what is coming at the same time, right? What you isolate, you put into the trap, and then as soon as you fill the trap, sooner you get not necessarily even saturation, but you fill the trap with any ions, and you cannot overload, right? So there is a caveat here in terms of you cannot overload the system, which you could still do here. But the advantage is if you can really select reasonably your precursor, you can trap it for a longer period of time and get very high sensitivity. You always collect full MS spectra. That means you don't have to worry upfront about which fragment am I going to use for the processing. You can do that subsequently. And in addition, then you have the multiplexing capabilities, which allows you, if we try to measure more, and especially this becomes interesting if we do quantification. The multiplexing has been used in DIA also to measure multiple precursors and get more spectrum measured at the same time. That's not what we're trying to do here. What we call multiplexing in PRM is basically in a targeted way measure a couple of precursors, typically the endogenous peptide and the corresponding internal standard, which we know exactly what they should like in terms of fragmentations, and we quantify them at the same time. And that allows to increase a little bit the duty cycle. So to summarize again, the PRM workflow is basically based on the high-resolution Orbitrap instrument. We measure full MS spectra, and as I'll show you this afternoon, we use also this MS spectra not only to make sure we have the right analyte before proceeding in the quantification, but we also will use them on the fly to actually use the system to decide should I or should I not measure, or should I do this experiment or put priorities, right? So the instrument can on the fly then make clever decision on what is important and what is not important. And that will be the topic of the session after lunch. And again, the main differences here between the two methods is in terms of experimental design. In a SRM experiment, you do everything up front. You start from your peptide, you use your reference libraries, you define all your parameters, you load everything, you collect, and eventually, once the collection is done, you have your data, And the processing, I'm not saying it is straightforward, but the tool are there. Basically, you can upload the files, and Skyline will then do all the calculation and give you the result. Now, you're happy with the result, or you're not happy with the result. If for some reason you have starting the hard interferences in your samples, the only thing you can do is say, I need another set of transitions, and you have to go back and redo the experiment, right? Recollect the data and measure everything. In a PRM experiment, basically we split the workload in two. The first one is just the same way as in an SRM. You define your peptide, you define when they elute, you just measure your full spectra at the right frequency and rate, so you have a good data set, and then the data processing comes and you select the transition. So typically what we do here is, and we're working closely with Brandon to make it directly interactive with Skyline, which works, but we also have to work on the next generation I'll discuss later on. But basically what you need to do here is take the raw data, and the two parameters you need to define is the windows for which you want to extract, let's say typically 10 ppm. And I showed you an example before where it shows you how the windows affects how you can look at the data and what impacts on the array data. And by default, we may extract 6 or 8 most intense transition, right? So they're already there. And then you generate basically an SRM-like file. You have your different traces, and then your system can just take 2 or 3 traces, depends on how you do. If you're not quite happy of these traces, you could just go back and require another set of traces and integrate it. But that means you collect the data only once, and then you have quite a bit of flexibility in terms of processing and analyzing your data. Right, and that basically everything I already said. So we now try to design a process. We do multiple experiments. We basically have all the raw files. We try to work out a script via Skyline, or first independently and then going to Skyline. Basically, you get two types of objects in this data. First, you get the full MS spectra, which have their utility, and I already discussed that. So MS spectra is actually a very useful set of parameters we have. And then you extract the traces of interest, you process them, quantify within Skylines, and eventually you have your result. You could further analyze clustering as everybody is used to do, using different tools for basically statistical analysis or clustering, or depending on what your application is. But basically you can very quickly and easily generate your result. So I hope in this first part I could convey some of the basic principle of PRM, and I think we all know that quantification in complex biological sample is and remains really challenging. It really requires high selectivity and sensitivity, right? And I showed you a couple of examples. If you would just look at the first signal you see, it's pretty obvious that actually you have clearly ambiguities and problems with sometimes the sensitivity, and more specifically with the selectivity. So high resolution methods, I believe now taking tractions have been shown. They are alternative to classical SRM. We can either do quite a bit of work using the SIM mode. Most people have switched to PRM, but there's still a few instances where actually the SIM mode can be useful, because you can get reasonably good resolution and separation, and the intact precursors actually give you roughly a factor 10 in sensitivity compared to the MS, right? Because on average you fragment your precursor in 7 or 8 fragments, and you distribute your signal. So if you look for ultimate sensitivity, a SIM is still a reasonable option. PRM, as we discussed, is looking at the fragment ions, and in terms of immediate benefits, right? Not going to repeat myself, but experimental design is very straightforward because you need fewer parameters. I showed you a few examples, and if we do larger studies, we really look at quantification across a large number of samples and CV you're really getting a dramatic increase in analytical precision, right? You really get CVs below 10% if you have the right setup and your right method. The point I already mentioned, you get high-resolution accurate mass measurement on any fragments and any precursor. So you are really confident in terms of elemental composition. That's what you measure, right? It is not a nominal mass, which could you can use that to assess or make sure you're measuring the right ion. And the method of acquisition is simple. We discuss that later, right? And the processing is also straightforward. I think the key issues which remains and is eventually the instrument getting better and better, and the ultimate problems, it was also alluded to the previous session, if we now really want to be quantitative, is sample preparation, that interval standard, and losses, and other things, right? The instruments are getting better and better. We solve a lot of problems, but eventually, I think if we really want to start and be really quantitative, we also have to address the very upfront, which is the sample preparation, and how we prepare the sample. So a couple of points I will address after lunch, since we're going to break up for lunch, is how we do the scheduling. So this in a similar way as you do an SRM experiment, you can schedule and break up your elution time, so that allows you to measure more peptides over time. We do the same thing here, apply exactly the same principle. How to actually multiplex heavy and lights and try to increase the number of measurements. And I'll show you example where we get up to 1,000 peptides in 1 hour runs. But it also then needs some clever on-the-fly decisions, and that's why I use the MSMS spectra. So that's why I was already insisting a little bit of not only just the traces, but actually the ion intensities or the ion ratio are actually quite important. And I guess I can take questions now, if there are some.
So fantastic. Thanks, Bruno, for this very clear, comprehensive introduction to PRM and also the benefits of being highly resolved in targeted proteomics. So do we have any questions? Yep.
Yeah,
would you mind take the microphone? Thanks.
I'm wondering whether the PRM only applied to the Q executive, which is Orbitrap system, or they also apply to QTOF?
So we did most of our work on the Q executive. So we optimized all the parameters and the method on the Q executive. In principle, you can translate most of the principle on the QTOF as well, right? So then everything which will be different is here we optimize the synchronization of fill time and acquisition. Or QTOF, you have to a duty cycle and you have to push your ions into the TOF system, right? Not necessarily to get exactly the same duty cycles. You have other limitation. And certainly what you do not have is you make it easier. You cannot play with the trapping time. So then basically it's one default parameters. But it could also be a drawback, because then if it still remains a flux system intrinsically, right? If you have very little ions, you may have a lower detection limit. But in essence, you could apply the same principle, right? And I mean, in principle, PRM is 20 years old, right? Because QTOFs have been 20 years old. It just, or even the Orbitrap was at least 10 years old, right? But it has only become a really implementable in such a setup, because you had to have a couple of things coming together, that the electronic and the speed goes fast enough, and then you can really synchronize all the ions, right? If the latest QTOF, I haven't really done the experiments. I think you can get reasonable result, but if you get to an older generation QTOF, I think it would be not very performing. At least you would not necessarily reach the level of sensitivity of a triple quadrupole. Right. That was always a little bit the bar, right? The reference is still the triple quadrupole SRM experiment. And if you put your parameters then there is always two setups, right? The default setup where you take your default parameters and you compare things together. That gives you one value. Now you can fine-tune either triple quad or an Orbitrap or a QTOF and get 10 times or 20 times better. Now, is that really representative of all experiments you want to do? Or every experiment is a weak tuning. So what are you comparing, right? We have to be a little bit careful when we start comparing platforms. What are the parameters and how much is, let's say, by default or easily accessible, and how much is postdoc time, weeks behind it, right?
We published a paper several years ago now about doing PRM. We call it pseudo SRM on an LTQ, and that worked fine. I mean, obviously, it's not going to have the selectivity benefits that you outlined, but it still is totally possible to do PRM on an LTQ, low resolution.
Yes, I think it's eventually a question what we define, right? If the principle you isolate and you measure, the principle is old, right? As soon as you have a high resolution, it's, if we now try to put the standard and try to match the best performance of the best triple or, let's say, this generation of PRM, right? So the bar is changing, right? But the physical principle, I agree with you. It's not new per se.
So since I'm sitting right next to Brendan, I guess I'll ask a question. So I was wondering how you actually do the 10 ppm extraction windows in practice. So you showed these really nice plots of a very clean trace when you move to 10. But it looks like you're using profile data from your plots above. So aren't you then, isn't your window actually smaller than the peak itself in mass to charge space with a 10 ppm window?
So we go back to the raw data and we look at the spectra, the 10 ppm, and we take that value, right, when we cycle to the spectra.
Right, but the actual signal that you're extracting in mass to charge space, is the width of that in mass to charge what would be a 10 ppm isolation window? Or are you like centroiding the data so it falls, the entire signal for your analyte falls in the 10 ppm window?
So we do either way, and we haven't yet a proper answer the benefits in doing one way or the other, right? And 10 ppm is, if we want to maximally optimize by default, we probably would still do 15 or 20 in the first run, and then a second refinement with 10 ppm.
Okay, thank you.
But this was data. But this was data from MS1. The selection window, the 10 ppm. You're recording MS1 and then you're doing MS.
No. So what I showed here in PRM, the MS1 is at best, by default, it is 0.7 Dalton. We can go a little bit lower, but the MS1 is not a high resolution mass selector. We can measure what we have isolated in high resolution and see what we have there. But the isolation of the precursor is still, quote unquote, low resolution because the quadrupole remains low resolution. Then we fragment and we get our fragment ions. And that's what we look at the fragment ions in the MS spectra. We know the mass and we try to target because it's a targeted mass. So we know the theoretical mass and we make sure the external mass is, let's say, within 10 or 15 ppm, and only that we would extract.
Sorry, I had another question. Sensitivity is one thing. What's your experience with validating quantification methods for assays that could be used in clinics? Do you follow the same FDA requirements for validation? Or are there changes to be done? Here you could, well, with PRM, you barely see noise. So you cannot even define a limit of detection. These kind of things. Do you have an experience or does anybody have experience?
So let's, I think it may or it will eventually make it to the clinic and to really validate an assay, right? The method per se is still fairly new, right? And it's still maturing from year to year. So there is, I think we understand much better today than 2 or 3 years ago, just the parameters and what it does. And we can start setting default values and parameters to do that. Now, if we do now really limit detection even with quantification, the way we do it, we do standard curve, dilution curve, and we try to see how far we can go. And when the signal, and actually have a slide, I didn't put in my deck here, but it shows that actually you have actually very good, you could measure very few ions, and it shows very big variance, but then the variance is not only due in this instance due to the fact that your ion count is too low, right? And the statistic doesn't apply anymore. But if you do the same experiment on triple, you start seeing very stable, but at least you start getting the noise is a rate limiting factor. Here is the number of ions in your trap, it becomes the limiting factor. So there is not a direct way of measuring the noise, but you still can measure the ion statistic. And you could see where your ions start having very large CVs. It means you have very few ions. And I'll show you a couple of examples later this afternoon, where actually you see you don't undersample of, and you add the limiter. You have then to tweak the system, get more ions to get. But to your question, FDA approved, I think there is still a little bit of homework to be done to get to that level.
I have a question regarding the method that you were showing. You had, I think, 8 peptides in 2 seconds cycle time.
Yes.
With 120 milliseconds. So do you do a MS1 scan in between? Because otherwise, if I have 8 peptides with 120 milliseconds, I should have a cycle time of 1 second.
8.
I don't know.
You're saying 8 times 120 doesn't give 2 seconds?
That's 1,000 milliseconds.
Then I ever had a typo on the slide.
Okay.
So that could well be. Yeah, then it was probably, yeah, this probably was.
But you do have an MS1 scan in every cycle as well anyway, or not?
No.
No? You don't measure any MS1
we don't necessarily do
scans?
MS1 because we don't use MS1 to trigger anything.
Right.
So we do, and we check if the peptide is there.
Okay.
And I'll show you later on how we actually now implement it more routinely.
Yeah.
So I have to check the slide. Maybe there is a typo in the slide.
So any further questions? Tina?
So Bruno, you show that the collision energy matters also a lot in PRM, and that you get these different ion intensities with 2 different values that you used on one slide. And in SRM, we always have these linear equations that we use to determine the optimal collision energy. How do you do it on the Q-exactive, and what's your experience with collision energy optimization in PRM?
I think it's let's say in SRM you would have the options to measure the different transition at different collision if you wish to, if you could, if it's really of a benefit. Here we're not necessarily using the default value. We typically, so in most experiments we really quantify. We have the reference peptide, or we know which peptide we measure, and we would typically at least have a measure at 2 or 3 collision energy and try to compromise to get the best intensities. But we have to compromise, otherwise if we would to measure a low and a high, it's really getting tricky and complicated. It's not doable. In SRM, you could individually set the energy if you wish to. Some people do, some people don't. Most Y ions are fairly well behaving, but we have cases where we looked at larger peptide or some proline peptides. Sometimes the default value is not necessarily the most optimum, and that is part of the optimization, to use potentially a slightly low energy. But again, that is basically part of an optimization. If you just do by default, you would work with the classical default value. But also the default value of the instrument that typically been set, or most instruments typically set for getting reasonably good fragmentation to get pretty good mascot score or identification, right? Sometimes less energy, a little bit less fragments, and more signal in the remaining fragments could be beneficial.
Okay, one more.
So assuming we have too many peptides to target, would it be possible to set a specific transient time and injection time for each individual peptide?
Short answer is yes, but you need to know which peptide and when. So that would make the method quite complicated. If you try to develop a method or plan it in the method, you can do it, but it becomes really quite tedious, right? Because the transient time or the field time also depend where you are in your curve, right? If you have the maximum concentration, you feel faster than you are at the beginning of the peak. So answers in principle yes, but I think it would be very tricky. And the answer to that is basically we do more dynamic monitoring on the flight, and we basically decide, and I'll show you that in the second part.
Okay, great. Thanks a lot. So we scheduled 1.5 hours for lunch, and we're a little bit ahead of time, so we can come back at 1:15 then, if that's okay for you, Bruno. Yeah. So back here at 1:15 for Bruno's second lecture. Thank you.